Critical Points and Local Extrema Part 1. In this video, we are going to do a number of definitions and some conceptual work. So, if you like to take notes, get ready to write a little bit. Suppose f of x is a continuous function on an open interval around x equals c. Later on, we will use notation similar to this. C is an element of parentheses a to b. We are saying the same thing, that c is some x value on the open interval a to b, meaning it's not one of the endpoints, but it is an x value on the interior of a to b. Our first definition, critical point. F of x has a critical point at x equals c if f prime of c equals 0 or f prime of c is undefined. We will use this a little bit later. But let's take a look at our next two definitions, which are of local extrema. Now consider x equals c, where c is on the open interval a to b. That's important. If f of c is greater than or equal to f of x, upside down a, meaning for all x on the open interval a to b, then f of c is a local, also known as relative maximum of f. If f of c is less than or equal to f of x for all x on the open interval a to b, then f of c is a local or relative minimum of f. What does that say? Well, if we look at it, where it says if f of c is greater than or equal to all other f of x, what does that mean? It simply means if I have a y value that's bigger than all other y values, then it's the biggest of f. In mathematics, we like to be precise with our language, but sometimes we disguise very simple concepts in a little bit more difficult language, if you would. Well, how about this next one here? If f of c is less than or equal to f of x, what am I saying here? If a y value is less than or equal to all other y values, then it is the smallest y value. Okay, that makes sense, and these are our definitions, but they're not very easy to use. So let's take a look at a picture down here. I recommend that you draw this picture. This is a graph of f of x. My question to you: what do we notice about critical points and local extrema of f of x, and maybe anything else that comes to mind? Let's start by labeling our critical points and our local extrema, or at least by finding them. I bet you would agree that right there you have a local maximum. I will abbreviate it as local max. That is, on an interval right around it, this open interval around that particular value, it is the highest value, the local max. Over here, I bet you would also recognize that we have a local minimum, which I will abbreviate as local min. That is, on an open interval right around that, that is the smallest y value. Do you see any other critical points? Remember that a critical point is when f prime is 0 or f prime is undefined. Well, I see one other critical point, which is right about there. In fact, now let's label, if you would, at least in a way, our critical points. Well, this local max is when f prime is 0, right? That is, f is momentarily flat or horizontal. At the local minimum, I see that f prime is undefined. And notice that I could have switched this graph around, where I had f prime undefined for a max and f prime equals 0 for a min. But I also see one other critical point. It looks like right about here, f is momentarily horizontal, so f prime equals 0. Now, one thing I notice is that local extrema only occur at critical points. Pick any other place on f. I'll just pick a random place here. That is definitely not a local extrema, because there are some values of f both higher and lower on the open interval around it. And notice that my function is increasing, or f prime is greater than 0. And I could do that anywhere that I wanted to. Like if I chose another point right there, definitely not a critical point. F is decreasing, or f prime is negative. Recall that f prime is a slope of f. So it certainly seems, and it is true, that local extrema only occur at critical points. But critical points don't guarantee local extrema. As we see by that one example that I placed in our graph right here. We have values that are both higher of f and lower on an open interval right around that point. It is a critical point, but it's not a local extrema. So local extrema only occur at critical points. That's going to become important. Critical points don't guarantee local extrema. Important, but not as important. But let's keep going. Let's take a look at our local maximum. Yes, there was a critical point, so it occurs when f prime is 0 in this case. But let's look right around that critical point, and I'll call it C1. What happens right around the critical point? Well, notice that my function is increasing right before it, f prime is positive, and then my function is decreasing right after it, f prime is negative. I will formalize that in just a bit. Similarly, for my local min, occurs at a critical point, in this case when f prime is undefined. I will abbreviate as UND. But look right here, I'll call this point C2. Notice that right before my local min, f was decreasing, meaning f prime is negative. And then right after my local min, f is increasing, or f prime is positive. So we formalize this in the following way. We call this the first derivative test, in parentheses for local extrema. Some conditions: let f be continuous on the open interval a to b, and differentiable on that open interval, except perhaps at x equals c, and let x equals c be a critical point of f, meaning f prime is 0 or f prime undefined. If there is a critical point and f prime changes from positive to negative at that point, then f has a local maximum. What does it mean? It means if we're going up and then we're going down, there's a local max. If f prime changes from negative to positive, meaning the function is going down then going up, then f has a local minimum at that point. Let's do a couple problems. Consider f of x equals x cubed over 3 minus 7x squared over 2 plus 10x plus 5. Find the local extrema of f. When we're solving problems, one thing we want to do is pick out our keywords or phrases. That happens to be my keyword or phrase. When I say keyword or phrase, since we're in calculus, it's a calculus keyword or phrase. It's not find, it's not function, it's something that tells me what to do in calculus. And local extrema of f says, I want to find where f prime is 0 or undefined, and then see how f prime changes right around that critical point. So it's a big keyword that says find f prime. So let's start by doing that. F prime of x equals x squared minus 7x plus 10. I have a polynomial which is always defined, so we will find when f prime is 0 only. This looks like it's factorable, which it is, so that's a good step to do. So we have f prime of x equals x minus 2 times x minus 5. I'm going to use a number line like this and place my critical values, x equals 2 and x equals 5, on this number line. And then I'm going to make a sign chart. If you haven't seen this before, the only places where my function, in this case f prime, can change signs is at the critical points. So we can choose any other x value on each interval and see what happens. For example, if I choose x equals 1, which would be right about here somewhere, and I plug x equals 1 into my derivative, I get a negative value times a negative value. The exact value is not important, just that we have negative times negative, which gives me positive. So at x equals 1, f prime is positive, which means any x value on this interval, f prime will be positive. Similarly, let's try a value between x equals 2 and 5, let's say 3. If we plug that into f prime, we get positive times negative, which is negative. Any x value greater than 5, let's do 6, plugging in, I get positive times positive. I won't write that down. I will just put down positive. I also like to put f up here because when f prime is positive, I know that f is increasing. When f prime is negative, f is decreasing. And now we have f increasing again. And so I get a pretty good visual representation of what's happening with f. And I certainly see up here that at x equals 2, f has a what? Well, a local maximum. Why? Because f prime is 0 and changes from positive to negative. My first derivative test. At x equals 5, f has a what? Well, it has a local minimum because f prime is 0 right here, and then f prime changes from negative to positive. That is, f changes from going down to going up or decreasing to increasing. So f has a local min. One more quick example. Consider g prime, which is x plus 4 times x minus 6 squared. And let's find the local extrema of g. Again, I'm going to do my number line to build a sign chart and put G prime here. I already have G prime. It's already factored, so I can put in my critical points right away, -4 and 6. I'm going to do the sign chart very quickly. If I choose a value, say x equals -5, I get negative times, well, that's always positive, so I get negative. If I choose, say, x equals 0 on this interval, I get positive times positive. And if I choose, say, x equals 8, I get positive times positive again. And then if I draw G, I get decreasing, increasing, momentarily flat, then increasing again. So the critical points of G in this case where G prime is 0, are at x equals -4 and x equals 6. But notice that at this critical point, x equals 6, there is neither a max or a min, which happens sometimes. But at x equals -4, we do have a local extremum. In this case, we have G has a local minimum because G prime is 0 and G prime changes from negative to positive, meaning G changes from going down, decreasing, to going up, increasing.